Video 6 of our transformation unit. We now get to talk about the true legitimate 100% transformer, Dilator. The only difference about him was, remember, he was a non-isometric transformer. He actually did change length and angle, not angle measure, but definitely length and size, while our isometric transformers just changed positions. They kept their size. So our isometric transformers are all congruent figures, and our non-isometric transformer, our dilator, will guarantee similarity, but not necessarily congruency. It could be congruent, but not always. So the definition of what a dilation really is here. A dilation is a transformation in which one object is larger or smaller than the other by a constant, and here's going to be the math part of this, multiplicative factor. So with translations, we added and subtracted to move the position up, down, left, right. But with a dilation, we're going to do nothing but multiplication, or its inverse, division. Now, here is our dilator. He doesn't look like much right now, and we've got a French fry guy over here holding an 18th century style kind of musket handgun here. But dilator is not scared of having a gun pointed to him because he can dilate. So dilator, do your thing, buddy.
Oh, and now I'm going to eat you, French fry. Gloop.
Bloop.
Ha 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 ha. Don't mess with me.
Well, that was interesting. All right, thanks, dilator. Every dilation has a center, and think of the center as the root from where it will grow or shrink from. It doesn't actually have to be on the center to grow or shrink from, but it's kind of like a focal point. If you know anything about drawing perspective stuff, you have to have a focal point where everything kind of draws to. That's the same thing as a dilation. And we have to have a scale factor that indicates how many times bigger or smaller, technically, dilator will become. So a dilation is called an enlargement, if we get bigger, if the scale factor is greater than 1. So if things get, if we multiply with something more than 1, numbers will get bigger. If we multiply by a number that's less than 1, but still greater than 0, technically things are going to shrink. And if we multiply something by 1, it stays exactly the same as it was before. So a dilation is a reduction, if it gets smaller, if the scale factor is, what I mentioned just earlier, between 0 and 1. Now, it can't be 0 and it can't be 1, so we would call between 0 and 1 exclusively. It cannot include 0 and 1, but it is exclusive to our two endpoints. So any fraction or decimal between, but not including 0 and 1, will result in our shape getting smaller. Now, dilations have rules just like we did with translations, reflections, rotations. For dilations, we're going to use a capital D for dilation, and then our scale factor is going to be this k value of x comma y points. And it's the same thing. This is just like the generic form of a dilation. If we just said x comma y, and if you notice that we're multiplying the x and the y by the same multiplicative factor, this k value, that is our scale factor. Now, this rule only works whenever the center is at 0, 0. So what happens if it's not at 0, 0? How do we do the problem then? Well, we'll look at some examples of those. But it really makes things a lot easier when the center is at the origin, or 0, 0. So our first example. What if we had a point, -5, 18, and we wanted to determine where it ends up at after a dilation with scale factor 1.42 with the center at 0, 0. Well, we don't have to graph this point because we're dealing with the center at 0, 0, so we can use the rule that k, our constant multiplicative factor, is 1.42. So, I mean, we are at -5, 18. All we're going to do is multiply the -5, and the 18 by our constant multiplicative factor. And so we'll see where does -5, so calculator, thank you. What is, oh, where are we at here? -5 times 1.42. Except you didn't do the 1, buddy. Let's try it again. -5 times 1.42. So -5 will move to -7.1. And then 18 times 1.42. Come on, where's the decimal point at there? Whoa, we're getting crazy now. 18. Come on, this calculator. I tell you what, guys. There we go. 25.56. And so there's where our dilation will end up at the point -7.1, 25.56. So don't be surprised if you see some decimal stuff going on or some fractional stuff. It's okay. Not everything's going to be a integer value, an integral value, like a ×2 or a ×3 or ×4, or maybe a ×half. We'll deal with some messy stuff in here. Second example. What if we knew the pre-image and the image coordinates and we wanted to know what the scale factor was when the center is at 0, 0? So again, we're still dealing with our same rule that we could use with our k scale factor. But if I knew I was at 5, -10, and then I multiplied by some value k in both of these, and that meant that I ended up at 17.5 and -35. Well, how could we figure out what that k, that scale factor, really is? Well, instead of multiplying, we're going to have to undo the multiplication to figure out what was being multiplied. And so really we're going to divide our image coordinates by our pre-image coordinates to figure out what that k scale factor is. So if I took 17.5 divided by 5, or if I took -35 divided by -10, both of these will result in the same number. And if they don't, then what that means is the center is not at 0, 0. So in both of these cases, I will get 3.5 as my scale factor. So things enlarged by 3.5 times their location. So again, if you notice that both, or however many points there are, well, really just 2 points, right? But if you notice that the scale factor is not the same for both, again, that means that the center was not at 0, 0. Example 3. Given we've got this triangle ABC, let's draw the dilation with a scale factor of 1/2 with the center at 0, 0. So we could technically use our rules here because our center is at 0, 0. And so if I just wrote down what the coordinates were, I'm going to show you this one of two ways here. So A is currently at 1, 2, 3, -4, 4. So -4, 4. And so if we multiplied this by 1/2 with our scale factor, then A prime would be located at -2, 2. So if I went -2, 2, there's A prime. And if I did the same thing with B, B is at the point 2, 1. And if I multiplied it by 1/2, well then B prime would be at 1, 1/2. So if I went over 1 up 1/2 unit, there's where B prime is. And then likewise with C. C is at 0, -3. And if I multiply its coordinates by 1/2, then C prime will be at 0, -1.5. So right here would be C prime. And so if I finally connect together my A prime, B prime, B prime, C prime back up to A prime, I will have my dilation with scale factor of 1/2 at a center of 0, 0. Now, we definitely know since our scale factor was less than 1, we should have had a reduction, and our image indicates that things did reduce in size. The other thing I want you to notice is that this triangle really is similar to our original pre-image triangle ABC. It is smaller, so it has that 1/2 factor, but all the angles maintained their measurements. So this angle up here by A is still this angle here by A, and this angle here by B is still this angle by B, and at angle C is still the same angle by C prime. So these two triangles will always be similar to each other. regardless of scale factor and regardless of the center. Another thing I want to point out is a different way of doing this problem altogether. And it kind of involves doing some slope stuff. So if I started at my center of 0, 0, I would have to go up 4, left 4, right? Up 4, left 4. So here's my center. If I went up 4, left 4, then really all I have to do to determine my image coordinate is I need to take half of both of these directions. So half of 4 and half of 4, well, that's easy. That's 2 and 2. So I should really go up 2, left 2, and there's where A prime is, which is still at negative 2, 2. So I could do the same thing with B. With B, I'd start at my center, and I would go, let's say, what? Up 1 over 2, up 1 over 2. So again, cut both of these in half, and then I'd really go up a half and over 1, right? Up a half over 1, there's B prime. And then last but not least for C, well, from C I just went down 3. So if I take half of that, I'd only have to go down 1.5. And there's C prime. So again, if I connect all those 3 points together, there's A prime, B prime, B prime, C prime, C prime, A prime, and it's the same triangle that I had before. So when the center's at 0, 0, you can use your rules, like we did the first time, or you can use your slope idea here and then just multiply the rise and the run part by your scale factor, and then determine where that image point will end up.